So I was staring at this subway map yesterday from a city I've never even visited.
Oh, the classic tangle of colored lines.
Exactly. It's
Yeah.
just it's
Yeah.
just abstract art. It doesn't mean anything until you have the legend, you know, until you know that a circle is a station and a line is a tunnel.
It has no truth without the key.
Right. And that is exactly what we're trying to figure out in this deep dive. How do mathematicians take this chaos of abstract symbols and give them a skeleton, a structure that actually means something?
It's the ultimate legend for the map of logic. And it all starts with this fundamental idea called a structure.
Okay, so a structure. Looking at the research, this isn't some vague concept. It's a formal blueprint with three really specific parts. First one is the domain,
Right, or the universe. And that's really just the set of stuff we're talking about.
the stuff.
Yeah, the actual elements. It could be all the real numbers or, a set of chess pieces. You just have to start with a bag of things.
Okay, so we've got our stuff. Then we need the language to actually talk about it. That's the signature, I'm guessing.
You got it. The signature is your collection of symbols. You've got function symbols like a plus sign or a multiplication sign, and then relation symbols like less than.
And they each have an arity, which is just a fancy way of saying how many things it needs to work, right? A plus sign needs two numbers.
Exactly. But here's the crucial part. Just having the domain, the stuff, and the signature, the symbols, it's not enough.
You're missing the connection.
You are. You need the third piece, the interpretation function.
Yeah.
This is the bridge. It's the rule that says this symbol, the plus sign, means this specific action of adding things together in this specific domain.
It's what gives the symbol its meaning. Otherwise, it's just a cross on a page.
Precisely.
So let's make this real. The source material brings up the standard signature for fields. So we have symbols for plus, times, 0, and 1.
A great example. Now, think about applying that same signature to, say, three totally different domains: the rational numbers, the real numbers, and the complex numbers.
They're all different sets of stuff, but they're all structures that use that same language.
Exactly. But here's the twist. What about the integers? The whole numbers.
Oh, yes.
You can view the integers as a structure with that signature. You can add integers, you can multiply them.
But they don't form a field. I remember that from algebra. They break a rule.
They do. In a field, every element needs a multiplicative inverse. You need to be able to divide.
And you can't divide 3 by 2 and stay inside the integers. You get a fraction. You've left the universe.
Precisely. So the integers have the skeleton, the structure, but they don't obey the laws of a field.
You know that distinction, having the setup versus actually following the rules? That's a perfect segue.
Oh, yeah.
It makes me think about our sponsor, Silk. Because if you're building a system for your business, maybe with AI or automation,
You don't just need the components. You need to know how they work together to actually get you results.
exactly, you need the right structure so the execution works. So if you're looking into AI agents or software development, check out embersilk.com to see where AI can make an impact for you.
So, getting back to that distinction, the integers have the structure.
But they aren't a model of field theory.
Yes. This is where we get to define truth in mathematics. A structure only earns the title of model if it actually satisfies the sentences, the axioms of a theory.
So truth isn't a feeling, it's a mathematical checkmark. Does this universe follow this law? Yes or no?
That's a great way to put it. The whole idea was really formalized by Alfred Tarski back in the 1950s. He called it the theory of models.
And you develop the satisfaction relation, which is basically the test.
It's the test. But now we have all these different universes, right? The reals, the rationals, the integers. Are they just stuck on their own islands?
I'm guessing not. The notes mention homomorphisms. These are like the boats between the islands.
I like that analogy. A homomorphism is a map between two structures that share the same signature. It translates the elements from one universe to another, but it has to preserve the relationships.
Meaning, if A plus B equals C in the first world,
Then the translation of A plus the translation of B has to equal the translation of C in the second world. It preserves the shape of the logic.
that's incredible. It means we can solve a problem in a simple, easy-to-understand universe and then translate the solution back to a much more complex one.
It turns a bunch of isolated islands of data into a connected continent of mathematics.
And that's the big takeaway for me. You have these three simple components: domain, signature, interpretation, and they create this universal language for truth and logic.
It's a powerful toolkit.
It really makes me wonder, if you can map the structure of one problem onto another, how many unsolvable problems in our own lives are just, waiting for us to find the right homomorphism.
That's a fascinating thought, that maybe the answer is just a matter of finding a new perspective, a new map to a world where the solution is obvious.
A hopeful thought to end on. If you enjoyed this deep dive, make sure to subscribe to the show.
And hey, leave us a 5-star review if you can.
It really does help get the word out. Thanks for tuning in.